Good morning and welcome to this new Bmax webinar dedicated to the simulation. We are very pleased to welcome you today. My name is Tabata and I am a member of the marketing team at Bmax. If it's your first time here with us, I advise you to watch our first webinar available on our YouTube channel. We are ready now to present the EHF process, and Gilles Mazars, the head of the simulation department at Bmax, will present a detailed study case to demonstrate our approach and expertise. During this presentation, if you have any questions, you can submit it in the private chat box located at the right of your screen. And if you are on a mobile version, you can find this chat box at the bottom of your screen. Gilles will provide answers at the end of the presentation, but if we don't have time to answer to every question, you will receive a personal response by email within tomorrow. I'm going to turn it over to Gilles now. Thank you for being here today. I wish you all a very good webinar.
Thank you, Tabata. Hello, I'm Gilles Mazars and welcome to this Bmax webinar about simulations. Today, this session is dedicated to EHF, Electro-Hydraulic Forming. It's the most versatile HPP process. We can use it for small sample, large panel, with one discharge or multiple discharge, and we can combine this process with stamping or hydroforming. So after a few words about Bmax, the company, its offer, will describe EHF principles. We describe simulation objectives and software and the special capabilities to activate to design these EHF processes. After, we'll present the main technical advantage of HPP impact forming, and we detail two case studies, one for luxury product, forming and engraving, and another one for aeronautic components, forming and calibrating. So, first, Bmax. Bmax has developed innovative processes and provides with equipment and solution services using high pulse power, HPP, for industrial applications. Basically, the product of Bmax is a pulse power generator which delivers an electrical energy, and we can plug this system on several devices to convert the electrical energy in mechanical energy and provide dynamic mechanical loading for manufacturing applications like forming, welding, assembling, and calibrating. To complete its offer, Bmax proposes any services in simulation, engineering, and training. There is two main solutions. Bmax can provide with equipment to deploy, to integrate in your plant, or Bmax can produce parts in situ in the Toulouse site. Regarding HPP processes have a small environmental footprint compared to usual manufacturing processes. Because they are compact, they have ultra-low energy consumption, there is no emission of chemical products and no heating, and the processes are quick and repeatable. EHF process. Yet an EHF system includes a generator and a final stage electrode system. The generator included a control cabinet, capacitor bank, and the trigger, the switch. And we plug the generator on an electrode system, and we put these electrodes in water to generate a plasma explosion. It's underwater explosion, and the plasma pushes the water surrounding the channels and create a pressure wave. The pressure wave is a mechanical energy, and EHF process consists to confine all these pressure waves to form a blank. The main advantages of EHF, like MPF, it's the speed of the process. It's a dynamic process. Compared to conventional forming process, the speed, where the speed is comprised between 0.1 millimeter and 10 meter per second, EHF, the speed in EHF can reach 100 meter per second, and in MPF up to 500 meter per second. So with this speed, we can change the process, we can change the structural response and material behavior. It's viscoplasticity. By this way, we can enhance the formability compared to conventional process. We create impact and we can engrave or create new texturing. and we create any stress through the thickness to change the stress distribution into the blank, and by this way we can change the nature of the springback. All is done in 100 microseconds. What is 100 microseconds? If you consider a bullet with a speed of 500 microseconds, it's the time to this bullet to go through a window, 5 centimeters. And in this time, all the forming is done. In this case, it's an aluminum plate, 410 millimeters in diameter, and the forming is complete in 100 microseconds. We have an excellent thickness distribution. We have no issue, no defect due to the springback, and we respect all the geometrical tolerance for this product. And we have a very good compliance between numerical result and experimental one. If you want further information about this case study, feel free to contact us. Simulations. The main objective of simulations. The first one is to understand the physics. HPP processes are multiphysics and dynamic, so it's very tricky to define engineering rules and to design this kind of process. That's why we use a computer and finite element analysis. Second, it's to build predictive model, to save cost and time, compare with prototyping. And the last objective is to answer to large customers. When we use innovative processes, we have to make the proof. We control our processes by simulations. We use LS-DYNA software. And we have simulation services, including STUDY, finite element analysis, simple approach or multiphysics approach, in static, in dynamic, regarding HPP or not. We have a team of experts in HPP, in simulation and conventional forming process. We propose numerical development for data processing, for example, and trainings. We are able to design any processes, standard processes or HPP processes, with 3 main steps: material characterization in static and dynamics, design and optimization, and technical support. If you want further information regarding the simulation service, you can take a look on the previous webinar on our YouTube channel. The uniqueness of Bmax is due to a long experience, 15 years of experience in HPP and simulations. We developed specific sensor and specific testbed, for example, to characterize in dynamics the materials, the material behavior. And we developed, regarding EHF, a specific model to calculate accurately the pressure wave generated in water. We have a PhD. We make the link between the electrical property of the HPP system and the pressure wave generated during the breakdown. It extends the equation of state of water to calculate the power released during the breakdown, and we use directly this power in LS-DYNA, in the software. EHF simulations. EHF, it's dynamics and multiphysics. Dynamics because all is done in 100 microseconds, and dynamics because we convert electrical energy in mechanical energy with the creation of pressure wave. Pressure wave is a mechanical energy. So the simulation tool has to be dynamic and multiphysics. That's why we use the usual dynamic mechanical solver of LS-DYNA to calculate the stress and strain in the component and in the blank, and we make a full coupling between ALE solver, arbitrary Lagrange and Euler solver, to have an Eulerian approach to be able to calculate the wave propagation through the liquid, water in the case of EHF. And we directly apply a coupling of this pressure wave on the blank, thanks to a fluid structure interaction. It's like a numerical contact. Here we can see a half model of a water tank on the top with 2 electrodes. In blue, it's the blank, it's the deformable part. And we want to push this blank, to form this blank in the green part. It's a rigid die. We perform an energy deposition, and all the fringe, all the colors are the pressure wave generated due to the energy deposition. As you can see, the first incident wave creates just velocity on the blank. We have a first reflection from the sidewall, And the combination of the second reflection and the top reflection, we can complete the forming thanks to the combination of last reflection. All is done in 280 microseconds. So it's one discharge, and we have a 3-step forming. So it's difficult to imagine such process without simulation. And as you can see, the loading applied on the blank depends on time and space. What are the main advantages of impact forming, like MPF and EHF? MPF and EHF deliver dynamic loading, dynamic mechanical loading, and it can change material behavior, the structural response, and the process itself. So these processes can propose other ways to form complex parts. First, the materials. Some materials have a stiffness which depends on the speed of loading, if you want. If we generate a high speed of deformation, high strain rate, we can increase the stiffness of the material. It's a viscoplasticity. Viscoplasticity usually can delay the necking, the critical thinning, and the crack. As you can see, with a very small viscoplasticity effect on the right, you can see just a simple tensile test. We can delay the crack on this sample. So viscoplasticity can enhance the formability. It's the first effect of the dynamic loading. The second, it's to change the structural response. If we consider two membranes, the same thickness, the same material, and the same pressure applied on this membrane. If the diameter is small, the stiffness of the structure is high, and the structure can catch all the pressure variation, and the maximum of pressure defines the deflection of this membrane. We have, at the end, the final shape, it's hemispherical. It's like hydrostatic forming, like hydroforming. But it don't require hydraulic press, a huge hydraulic press, and it's done in a few microseconds. But it's exactly the same structural response, like static. If we consider a larger diameter, big diameter, the stiffness of the structure is reduced, and the more sensitive parameter of the loading is the momentum. We create initial velocity. So the deformed shape of the blank during the process, it's a flat deformation, constant velocity, and at the end, the final shape, it's conical. So it's a dynamic structural response of the blank. Thanks to dynamic loading, we can change the stress, the strain, the deformed shape, and by this way, we can enhance the formability. Another effect of the dynamic loading, it's an impact. Thanks to impact, we can create compressive stress in the blank, in the material, in the sample, at the interface of the impact. By this way, a compressive stress can lock any cracks, can collapse the cracks, and by this way, we can enhance formability. With velocity at the impact, a few tenths meters per second, for example, we can create megapascal of pressure. With the high pressure, we activate hydrodynamic behavior in the materials. The behavior of material is like a fluid, even if thermodynamically it's a solid. In terms of pressure and temperature, it's a solid, but the behavior due to high pressure is fluid. By this way, we're able to engrave and to print any texturing on the blank. The last point regarding the impact, it's the creation, the generation of compressive stress through the thickness. If we consider stamping, forming with a lot of tensile stress along the fiber, a compression along the thickness can remove all the stress. So by the impact, we can change the stress distribution in the blank, and by this way, we can change the nature of the springback. But this impact is not constant in time and in space, as usual. So we can have an ironing. Ironing, it's a progressive contact closing, a progressive impact in a dynamic process. In this example, we have a first impact on the side of the blank, and this impact, the contact closing, comes from the side to the middle of the blank. And by this way, we push the material in the middle of the blank, and we can change the thickness distribution. By this way, we change the formability of the materials. And if we compare this test with a static bending test, at the end of the bending, we have an opening on the blank in static. The curvature of the blank is less important compared with the curvature of the die. And in dynamic, it's not the case. In dynamic, we have a closing of the blank. The curvature is higher compared with the die curvature. So we change, it's very specific, and we change the process itself due to the impact. The last advantage, it's a one-side loading. Compared to stamping, we use in stamping two tools, the punch and the die, and we create friction contact between the punch and the blank and the die. In EHF or MPF, we have just one contact. So in this example, it's a cavity in copper for the CERN. We perform a microstructure analysis to check the size of the grain and to verify the material property. Due to compressive stress into the material and no contact on the inner skin of this product, we have better material properties with EHF compared with mechanical spinning. So just for information, the cavity formed by EHF obtains the best result in the world in terms of performance for the CERN applications. Now let me introduce the case studies. The first one, it's a luxury product. Bmax enhance the luxury experience and reinforce the value perceived by the customers. Thanks to EHF, we can create new texturing and engraving with a high level of finishing on a complex part. By this way, we can replace plastic components and Zamac components by aluminum. This first example consists to engrave the George Adore L'Or cap. The material it's 5657 aluminum annealed and with 0.8 millimeter thick. The objective is to replace the plastic casted part by the aluminum, and we designed the EHF process to produce with a high production rate, 70,000 parts per week and 1 million parts per year. The first step consists to perform the material characterization in the static and dynamics. The aluminum 5657 annealed has been chosen by the customer to do the brightness after anodization. We define the material curve, the strain hardening curve in static and dynamics, and we track when the necking occurs to define an elongational break with high strain rate. It's 35% in this case. And we use all this data for the sample on the right. After we perform 2D simulation to optimize the condition to maximize the efficiency of EHF process. On the left side, it's a very simple preform geometry. And as we can see, at the bottom of this sample, we create a necking, excessive thinning, and there is a very high significant risk of crack. So the iteration consists to create a bump in the bottom of this sample to have extra materials. And by this way, we have a good process, a good deformation during the process, and the corner of the blank match with the corner of the die. And by this way, we reduce the maximum strain, and we fix the crack issue for this process. After, we perform 3D simulation to validate all the design, all the components in the system. And we can use this simulation result to analyze what's happened during the process. On the left side, it's a pressure wave generated in water into the sample. And on the right, it's the deformation of the sample in the same time. So at this time, we have a pressure wave, incident pressure wave, which comes from the electrode system into the sample, create a dynamic structural response. We have just initial velocity on the sample, on the top of the sample. We have no large displacement and deformation. By this velocity, create an impact, and we start the engraving of the sample. And we generate in water a very high pressure. All the color are, the pressure, magnitude of pressure, it's 1,000 to, from 1,000 to 6,000 bar. And this new pressure in the sample initiate the Aeronautic. And we have a first engraving of the sample due to this wave propagation into the sample. We reach the critical area. Here we have a static structural response. We create very high tensile stress in the fiber of the sample, and we remove all the detail formed before by the Aeronautic. In addition, we create a buckling. This buckling generates a high velocity and an impact on the die. At this point, we have paid attention to the stress generated in the die. As you can see, the pressure wave generated in water are very high, more than 6,000 bar. And this pressure wave propagates from the bottom to the top of the sample. And this pressure wave creates a new Aeronautic and the final engraving of the sample up to the top. So thanks to this analysis, you can take a new look on this process. You can see the difference between the inner skin of the sample and the outer skin. It's an effect of the one-side contact. In the real world, we use exactly this preformed geometry with the bump in the bottom. And we have the sharp details, the depth of the sharp details is around 1 micrometer. So, as you understand, for this kind of application, the preformed geometry is the key point. We have to optimize this preform to define the optimized initial condition for EHF. We are able, with EHF, to create new texturing, to engrave complex parts with very high marketing requirements. And we can form any products like fragrance cap, jewelry, luxurious packaging, cosmetic, and luxurious decoration, for example. If we analyze the takt time, one part is formed in 18 seconds, and we can imagine if the conventional process consists in machining, 1 or 2 hours would be required to form the same detail. So thanks to EHF and Bmax solution, we can reduce the scrap, we can reduce the lead time for production, and we can reduce the material consumption. The next movie shows the real automatic system developed for this production, but it's adapted to Bmax Goody. It's a USB memory stick. Now we'll introduce the second case study about aeronautic components. Bmax proposes advanced design solution to enhance the production of aeronautic components involving the process optimization and high scrap rate reduction. Thanks to Bmax solution, we can reduce the cost and the lead time for production massively compared to other conventional forming processes in aeronautics. The example here is a turbulence plate. Material, it's a cobalt nickel chromium tungsten alloy, 218 mm in diameter, 0.8 mm thick. The objective is to design and to optimize an hybrid process as stamping EHF process. It's a Bmax patent. The first step consists to characterize the material in static and in dynamics. This cobalt nickel alloy is sensitive to the strain rate. There is a viscoplasticity, and we can expect an enhancement of the formability. We use all this data, material data, to represent the behavior of the sample on the right. There is an existing process to form this part. The customer described 5 forming operations, and 2 thermal treatment. The first operation consists to a preformed geometry. The second one, it's the forming of internal area by expansion. The third, it's the forming of external area. At this point, the customer proceeds to a thermal treatment to relax all the stress in the blank before to perform a calibration of the external radius. After, there is a trimming of the blank before a global calibration of the conical shape. The requirements are the minimum thickness and a set of geometrical tolerance. With this process, the main issue is a significant risk of crack at the junction between in the radius, R3, at the junction between the vertical wall and the conical shape. At this point, the thickness is less than 0.57 millimeter. By this way, the customer has 10% of scrap for this material after sheet metal working like armoring, for example. In Bmax, we developed a specific ESH process by 2D simulation to save calculation time and to perform a lot of iterations. This iteration consists to optimize all the settings for stretch draw, the first operation, and for EHF. The stretch draw defines the initial condition for EHF. By these simulations, we validate the feasibility of this product by this process. After we perform 3D simulation to validate the design of the real components, and we describe the real operations. The first one is a stretch draw combined with the stamping, and we remove the punch, and we can proceed to EHF. We perform 8 discharge with explode wire. Here is the same simulation. The fringe, the colors, represent the velocity of the blank which impact the die. We can analyze the process thanks to these simulations. The discharge creates a velocity, a dynamic structural response. And with this velocity, we have an impact of the blank to the die. And we initiate an ironing. We create compressive stress. We calibrate the blank, and we propagate these impacts, the contact closings, and the calibrations. At this time, we have an impact on the vertical wall, and this impact creates a second ironing. All the ironing converge to the radius. And we push the material in the radius to have extra material and to limit the thickness reduction on this critical area. At this point, we have a static-like structural response. It's an expansion in the radius. We form the radius, and we create a lot of tensile stress on the vertical wall, and we have a small drawing at this time. After we have an impact in the radius, and we calibrate this area, and we propagate this impact, this contact closing on the vertical wall to complete the forming and the calibrations. In the real world, we proceed to this two-acting process with the stretch draw combined with a stamping. As you can see on the left, we have a blank holder. The blank is clamped between the blue and the red part. And this area is not submitted to EHF calibration. That's why in the real world, we proceed to thermal treatment to relax the stress on this area and to avoid any defect at the spring back. When we produce all these parts, we perform any 3D scan to check if we respect the geometrical tolerance. We're cutting any samples to compare the thickness between experience and simulations. The table summarizes all this data. We have a very good compliance between numerical result and experimental ones. All the gaps are less than 6%. We can pay attention on the third point. It's the radius, the most critical area for the conventional stamping process, where the thickness was around 0.57 millimeter. In our case, the final thickness is 0.77 millimeter. Remember, the initial thickness is 0.8 millimeter. So we have no thickness reduction on this area. So with EHF, we have no scrap, and all the parts are 100% compliant with the geometrical tolerance. When we compare the conventional process and hybrid EHF process, the conventional process includes 5 forming operations, 2 thermal treatment, a lot of defect due to the spring back, 10% of scrap, and sometimes it requires any metal working hammering. a part is produced with 13 to 15 hours. In SEHF, we have two forming operations, one thermal treatment. We have a good compliance, perfect compliance with the geometrical tolerance, and no defect due to the screen back, no scrap. And a part is produced in 3.5 hours. According to the customer, we can save 50% of the cost for production to produce this part. This SEHF example, the turbulence plate, it's a successful example of the use of SEHF process to form and to calibrate. But HPP solution offer a large range of solutions to proceed to forming and calibration for aeronautic components, for aerostructure or part engine. According to our experience, we can reduce by a factor 2 the cost and the lead time for production compared with conventional processes. Small remark about special process in aeronautic. For special process, the result cannot be verified by means of controlling or non-destructive test on the product. So the consequences of deficiencies can just appear during the use of the product. So according to this definition, SEHF is not a special process. It's a peculiar process, and the customer have to qualify and to approve this process. In conclusion, the two case studies are different examples, successful examples of the using of EHF. The first one, it's a luxury application. It's a Georgia dollar cap, where the objective was to proceed to engraving and forming. The material is aluminum, and we use a pure EHF with one discharge between electrodes. The second case study was a turbulence plate, it's an aeronautic component, in cobalt nickel alloy, and we designed and optimized a SEHF process in hybrid solution using 8 discharge with exploded wire. The objective was to form and to calibrate this part. In these both examples, we use simulation to understand, to predict, to design, and to optimize. The next webinar will focus on another Bmax solution to highlight the benefits of HPP and simulation. Thank you very much for your attention. Now, with Tabata, we are going to answer to your question.
Thank you, Gilles, for your presentation. So this is the time for the questions. We received some few questions, and the first one is, can EHF replace all the other forming process?
No, not really. MPF and EHF, for example, are not well adapted for deep drawing. Dynamic loading can lock the blank and limit the drawing of the material into the die and can create a necking, a critical thinning, and so on. So clearly, HPP forming processes cannot replace all the conventional processes. Another example for luxury products, the preformed geometry, the sample, is always produced with a conventional process. But we can combine HPP processes with conventional ones to take advantage of each one, and we can enlarge the possibilities, and we can use HPP to complete the forming and to engrave or calibrate. We cannot form all a certain level of thickness, but we can address a large range of materials.
Is the simulation phase systematically necessary?
In theory, we can perform the test without simulation, but it could be expensive and tricky to find the correct set of parameters to optimize the conditions. Simulation is a breakthrough. As we said before, we can predict, design, optimize thanks to the simulation, and we can reduce the number of tests. And by this way, save a lot of time and cost. In Bmax, simulation is always used to validate design. If the process is well known and required an existing process without modification or upgrade, we can imagine to do the test without simulation. But for all other cases, it's better to do it.
Another question, what are the materials for which Bmax has data?
After more than 15 years of experience, we capitalize and we fill a material database in, including static properties, dynamic properties in function of strain rate, anisotropy, viscoplasticity, and sometimes forming limit curves. These data can be the property of the customer if they wish to do so. And today we have a large range of materials like aluminum, steel, copper, cobalt nickel alloy, and so on.
And if high-speed material data is unavailable, what is the time and cost to determine this data?
For static and dynamic identification, the usual time frame is around of 2 months. Regarding the cost, it depends on the material properties, if it's a good electrical conductor or not.
Yes, and
it depends, yeah.
Sorry, if you want more information about this, you can contact us directly by email.
Yes, exactly.
Next question, does Bmax have the tools, means and skills to perform hybrid process simulations?
We have a team of experts in forming and in simulation, and we can design and optimize conventional forming processes. We are able to define the best way to combine HPP with the conventional process. In Bmax, we have a workshop in Toulouse with HPP systems, generator, switch, workstation, and so on. And we have several hydraulic press, fluid and vacuum units, and we can perform tests and produce any product scale 1 for automotive or aeronautic applications. For luxury product, special automatic system has been developed with all capabilities and all capacities included. Bmax can deliver HPP system and also can produce any parts.
What are the differences between electrodes and exploded wires?
There is several kinds of discharge using electrodes, but the principle is always the same. We create a water ionization and a plasma. And this plasma, it's a plasma explosion and a water explosion and push the water surrounding the plasma channels. And by this way, we use this pressure wave in EHF. With exploded wire, it's not exactly the same principle. A small copper wire, a small diameter, is used like a fuse, if you want, electrical circuit breaker. And we apply all the current, the electrical signal from the generator on this small wire, and we create a sublimation. It's a phase change, so from solid to gas, and ionization of the copper. And by this way, we create plasma, and this plasma pushes water and create pressure waves. The main difference between these two kinds of discharge, it's the fluid control. For electrode system, we have to check the pressure and the electrical conductivity of water to maximize the efficiency of EHF. Regarding exploded wire, it's more versatile and we can use a large range of fluid and a large range of thermodynamical conditions, temperature and pressure.
And can you tell us how many discharges can be used at the same time?
In theory, there is no limitation. It depends on the material of the product, its size, and the process itself. But usually, we try to minimize the energy level, the number of discharge, and the number of shots. For more complex applications, large dimension, or with high-strength materials, we can use up to 8 discharge without any change on the generator in the same time, 8 discharge on the same time.
This is a very interesting question. Are there limitations for forming regarding materials, size and thicknesses?
First, compared to MPF, EHF efficiency doesn't depend on the electrical conductivity of the materials. After, we can address large dimension up to 1 meter square, 0.8 meter square. And for stiffest material with high yield stress, for example, stainless steel or special steel, we test successfully 1.5 millimeter thick blank, and for softer materials like copper or aluminum, up to 2.5 millimeter or 3 millimeter thick. For luxury good, for small volume, we can use pure EHF. Small volume, it's few centimeters. It's a small volume, few centiliters, small bottle or cap, for example. We can form with pure EHF. For larger volume, we can implement hybrid solution, usual forming to form the part, to form the volume, and EHF to engrave.
What are the main issues regarding EHF use in industry, and why is this technology not democratized today?
Water. Water is the most important issue in the industrial environment. After 15 years of experience, Bmax proposed today industrial solution to fix this issue. And with the repeatability of HPP system and the lifetime of HPP components, we are able to enlarge the production using HPP for more and more applications. No one has developed this technology as much as Bmax did. So simulation and EHF are core business, and today we are intending to grow and to make these processes successful.
Next question, how long is the development time required between design and production of a product in EHF? And can it be compared with a conventional forming design?
Yes, we can compare the development time between EHF and stamping, especially for hybrid solution. Because for hybrid solution, when we combine conventional with HPP, the main part of the development consists in the definition of the conventional process to create optimized conditions for EHF. So the development time depends on the scope of the requirement of the process itself, and it could be a few weeks, 6 to 10 weeks, for a prototype way, and it can be more than 30 weeks, much longer, for industrial phase to mass serial production.
Yes, and you can also contact us if you want more information
Yes.
about this specific subject.
Sure.
What is the scattering of the process? Is it creating more scrap compared with usual forming processes?
A lot of scrap, a lot less scrap in HPP. We can, if we compare with conventional process, for very complex parts. Regarding production of aeronautic components, the usual geometrical defect due to the spring back create a scrap with conventional process. And this issue is reduced or removed thanks to HPP calibration. So the scrap is limited, and we can avoid a lot of hours of hand sheet metal working, like hammering. A lot of hours can be saved. So if we have the correct design and the correct settings, HPP processes are very repeatable.
What are the die materials? Are they the same than the ones used in conventional forming, or are specific surface treatments mandatory?
The key point with HPP impact forming is the impact. With high velocity, we can create good condition to engrave and to calibrate, but the issue is to create high stress in the die. So we have to adapt the material of the die to this special issue. We use special material like steel, but it's the same material compared with usual trimming operation, cutting operation. So if we consider the tooling, we have a one-side loading, when we need just one tool, one die, and not a punch, compared with stamping operation. And by this way, HPP can be cheaper.
Thank you, Gilles. This is the last question. So what is the price per part compared to conventional forming?
According to our experience, EHF can be 50% cheaper than conventional.
Thank you, Gilles, for your time.
You're welcome.
So this is the end now. As I said at the beginning of the session, don't worry if your questions were not answered, because our experts will give you a response by email in the 24 next hours. We hope you enjoyed this webinar, and the next one will take place in February, so stay tuned on our social medias and websites. Thank you again for your participation, and we hope to see you soon.